No. All right, I'm recording for all the good friends at home who are taking their exam so they can watch this, because I'm sure they will.
They're not gonna watch it.
Oh, yes, they are. All right, so instead of making you torture your way through this, I'm gonna just walk you through it myself, okay? So let's go over to a blank page and we'll try it. Okay, so there's the problem. Find a basis for the orthogonal complement. All right, so what is the orthogonal complement? It is the set of all vectors. Yeah, hang on one second. Thank you for the reminder. It is the set of all vectors z, and I wasn't, am I? Yeah, I'm screen sharing. Set of all vectors z such that the two vectors that I gave you, 1, 2, 3, 4, dotted with z equals 0, and 0, -1, -2, 3, dotted with z must equal 0. These two things must be true. Okay? So give me some advice for how you think we should proceed. Only 8 students. Someone's got to participate. What do you think? Should I cold call on someone? James, what do you think we should do to find those vectors z?
I didn't watch the Edpuzzle videos. So.
That's okay. Thank you for your confession. How many components will z have? Let's start with that. Does it have 1, 2, 3, or 4?
4.
4. Good. So let's call z x, y, z, and w. Okay. Yeah, we're going to make a system. See, it's that easy. X plus 2y plus 3z plus 4w equals 0. And then -y minus 2z plus 3w equals 0. So we have a system with 4 unknowns and 2 equations. And then, of course, at this point, my goodness, it's the same as everything this year. Ref, right? So we've got a matrix 1, 2, 3, 4, 0, and then 0, -1, -2, 3, and 0. So it's a homogeneous system. We know it's going to have some non-trivial solutions because we've got some free variables in here, right? So let's ref it. You can just sit back. I'll do all the work. Okay. Oh, that was my reminder to record, and I'm actually doing it. I'm so proud of myself. Turn off my alarm. There we go. Okay. Yeah, I was doing algebra studies today. Okay. RREF. It's hard, yeah. It's
Well, the concept itself is. Well, the concept is factoring is hard. Like, I don't know how to explain it to someone who's like, you just gotta do it. But like, who like intrinsically understands math.
I know.
Like, someone who like struggles with math is really hard.
well, here's the hardest part. When you say to your class, give me 2 numbers that multiply to 8. And there's silence. Like, how do you teach factoring if that happens? You know? You don't, right? It's just impossible.
I taught my little brother who's 7 how to do algebra. Yesterday. He was doing it
Like what? Like solving for a variable?
Yeah.
Yeah.
We were doing a math game. He was doing a math game on his iPad.
Mhm.
The question was like, it was like 13 minus what equals 4.
How old is he?
He's 7.
Oh, nice.
And I was like, okay, here, I'll write this down. What a variable is. He's like, oh, that makes
Good
sense.
job. That's cool. Okay, so let's write this as x1 equals, oh, you know what? I should have used x1, x2, x3, x4, whatever. So x1 is x3 minus 10x4. x2 is -2x3 plus 3x4. And x3 is free and x4 is free. Okay, so we're ready to create a basis now. That means that every vector that lies in the span of the 2 vectors I'm about to write is in the orthogonal complement. So W perp, remember that abbreviation? The orthogonal complement of W is the span of the 2 vectors 1, -2, 1, 0. That's all the coefficients of the x3. And then -10, 3, 0, 1. So if that's W perp, the basis for W perp is just these 2 vectors right here. Let's pause. You can ask a question if you want, or I will show you some examples on the calculator of how this works. Okay. Okay, so here's what W perp means. Any vector in W, and W is the span of these two, must be orthogonal to any vector in W perp. So let's confirm that that's true. We're just going to do an example to show it.
Graphic.
So yes, graphing it is an excellent idea. So I'm going to take a 4x1, 4x1. And can you read it to me? What was the first?
1, 2, 3, 4.
Oh, thank you. So I'm going to multiply that by -5. And then hang on, let me get the other one up and ready. What's that one?
0, -1, -2, -3.
Thanks. And I'm going to multiply that one by
The
16.
3 is constant.
Oh, thank you. Thank you. Okay, so this vector I'm about to create lies in W. All right, this thing is a member of W. Now I'm going to create a member of W perp, and we're going to show that the dot product of those two vectors is actually 0.
Just
Okay,
to clarify, just do the dot product, it's like really just the multiplication of the transpose.
correct. Okay, so our vector in our first basis vector is 1, -2, 1, 0. 1, -2, 1, 0. And I'm going to multiply that by some random scalar. What's your favorite number?
4.
4.
Not actually.
And then we'll multiply the other basis vector, which is -10, 3, 0, 1. What's your favorite number?
7.
7. There we go. All right, so my claim is that those two vectors that are sitting right there should be orthogonal to each other. So dot product of the answer and the thing up above should be 0. Let's pray. No prayer needed, it works. Okay, so it works.
Doesn't matter what scalars you put on.
Exactly, right? We just picked those totally randomly, right? We just found a vector that lies in the span of the two vectors for W perp. And up above that, we found a vector that lied in the span of the two vectors of W. And so that's kind of confirmation that we found the orthogonal complement.
So like essentially all linear combinations of the new set are orthogonal to all linear combinations of the previous set.
Well said. Let's write that. All linear combinations of the new set are orthogonal to all linear combinations of the original set.
Makes sense.
Good. And look at the dimensions. Look how they worked out, right? We were in R4. We had a two-dimensional subspace, and then W perp was a two-dimensional subspace, and this is always going to happen. The dimension of W and the dimension of W perp are going to add to whatever space we're in. So we're in R4, so we're going to add, those are going to add to 4. Zoom friends, do we have any questions here? Okay, cool. All right, what's next on my agenda? Lecture on, do you guys remember what this symbol means?
Section.
Section, good job. Section 6.2 orthogonal sets. All right, let's see how far we get. I have the most like clean lecture notes ever for this section. I don't know why I was so motivated in previous years to like get these.
That's how we're going through it.
That's why we're doing it. Yeah, exactly. I don't want to waste my really good notes.
Well, yeah, every year it must be like cutting it close but not using them.
It is. You're exactly right. And so I think one year I was just like, I'm frustrated, like giving this section like, a cheap shot. I want to actually like invest in it and make it good. All right, so label it 6.2 orthogonal sets. This is going to be like the cleanest lesson we've had in like months, with occasional interruptions for random conversation. And who's leaving? Who's leaving soon for the econ test? James, you said you are, right? Is that it? Is anybody else leaving for the econ test? Okay, sounds good. All right, cool. Okay, so here's the definition. Ready? A set of vectors U1 to UP. So the set is arbitrarily large. That means there's P vectors in it. And those vectors exist in N space. So we're going to say in Rn. So a set of vectors U1 to UP in Rn is an orthogonal set if each pair of distinct vectors from the set is orthogonal. All right, well, that's the definition. The lesson's over. That's the title of the lesson, right? All right, no, sorry, it's not that easy. Can you think of the easiest example of an orthogonal set that we've kind of worked with here and there throughout the year? What's that?
2 planes.
No, those aren't sets of vectors. A plane isn't really a set of vectors. It's right. It's a finite set of vectors.
Oh.
P is the last one, so it might be a set of 3 vectors. What do you think? We should think of the letters I, J, and K. What do we call that set? The basis, yeah, the standard basis vectors, right? They're mutually orthogonal, aren't they? I is orthogonal to J, and J is orthogonal to K, and I is orthogonal to K, right? So one example, so here's an example of one, would be the set I, J, and K in R3. Draw yourself a little picture of the 3D coordinate system, right? If this is the I unit vector, that's the J unit vector, and this is the K unit vector, they're all mutually orthogonal. That means that every pair is going to have a dot product of 0. Okay. So questions could be as simple as, is this set an orthogonal set? Okay, so that's one example. So question example. This could be potential quiz question, potential homework question. Just, is blah, blah, blah an orthogonal set? Okay, so how do we do that? You tell me.
There's the long way of taking the dot product of
That's the only way. Yeah. Were you thinking of a different way?
I don't know, maybe there was another.
Yeah, no. So that's the only way. If there's 5 vectors, you have to pair them all up and see if they're all orthogonal.
That seems like fun.
So, but you
Is
know,
there like a
that's-
command on the calculator?
that's a great question. I don't think so. Not that I can. I mean, we can look in the vector menu.
I mean, what you could try doing is making an infinite summation.
Ooh, that's an interesting idea.
Summation, not even infinite, like infinite, just do a summation of like indices.
Yeah.
That'd be stupid.
Nope. There's nothing that'll help us there. What about an advanced? Nope. Oh, there's our command for char poly. Didn't realize it was in there. Element operations. No. You'd need some more advanced programming to test it, to kind of go through everything, like you're saying, like right with it's kind of a cycling through an index.
Yeah.
You can do eigenvalues. Oh,
Yeah. Did I never teach you that command?
no.
Oh, sorry. Okay, any questions so far? So that's easy. It's just a definition. Any questions? All right. Assuming no one's read the textbook.
Nope.
Good. All right. What would your guess be is the next thing that we could conclude about an orthogonal set? Where do you think this leads? What else is true about an orthogonal set?
Spans the entire space.
Spans the entire space. Well, I can think of a counterexample really quick.
Oh, just I and J and. the
Yeah,
three
I and J in 3 space. They're orthogonal, but they don't span the entire space.
It's linearly.
Yeah, good job. Yep. So this is interesting. Every single orthogonal set, no matter how many elements are in them, is automatically linearly independent. Okay, we're going to prove that. The proof is easy enough for us to do. Okay, so let's state it as a theorem and then we'll prove it. So this is a theorem, and it says this: if the set S, which is composed of p vectors in Rn, so if that set is an orthogonal set of non-zero, that's a key phrase. Why is that key?
Because the dot product of any 0 is all automatically going to be
Good,
0.
good.
That's the means orthogonal.
Good. And what else? Every set that contains the zero vector is linearly dependent. So if David said that what we're going to show here is that it's actually linearly independent, that we must exclude the cases that contain the zero vector. Because really, any set that contains the zero vector is an orthogonal set, but then would not be linearly independent. So we have a set, it's an orthogonal set of non-zero vectors, okay? Then S is a linearly independent set, and hence a what? Can you guess?
Invertible.
Good. You could say that it would create an invertible matrix. Good observation. But the conclusion we're making here is hence a basis for the subspace spanned by S. Okay, so write that down. Let's get the fact out, and then we're going to prove it formally. Does anyone on the call today, I'm going to ask a Zoom person to contribute here. Does anybody remember the formal definition of linear independence? I mean, we've worked a lot with it, but what was the formal definition? Yes, Izzy, pivot in every column is part of the story, but I wouldn't call that the formal definition. Anybody else? Good job, Izzy. Only the trivial solution. Okay, so here's the proof. We're going to start with the equation 0 equals C1U1 plus all the way out to CPUP. With scalars C1 to CP. Can you please put a vector hat over the zero vector? So the zero vector equals C1U1 all the way out to CPVP. Or CPUP, I mean. All right, so the question is, that equation can exist, but the question is, does this equation have any non-trivial solutions? If it does, then the theorem is wrong. And if it doesn't, then the theorem is true. Okay, so we are hoping to show that the only solution, the only scalars that will make this true are when C1 is 0 and C2 is 0 and everything through CP is 0. In other words, we're trying to show that all of these C's have to simultaneously be 0. All right, here's how we're going to do it. We're going to say that the zero vector dotted with U1 equals 0. Of course, that's true. The zero vector dotted with everything is 0. And then we're going to be kind of sly, and we're going to take this whole expression and put it in place of the zero vector. Okay, so look what that's going to become. It's going to become C1U1 all the way out to CPUP dotted with U1. Now, this is where those silly, trivial facts actually are important. You know, we're always like, oh yeah, they have all these properties and we kind of never write them down, but I always say, well, they're going to come up at some point. This is one of those times. Because that dot product can really be written as C1U1 dotted with U1. And then I'm going to write a couple more terms just to make this clear for us. C1U2 dotted with U1. All the way out to C1UP dotted with U1. Here's another one of those trivial facts that seems frustrating to have to know and write, but it comes up in this proof.
Wait, why is it C1?
I meant C2.
Okay.
Thank you. That should be C2 and this should be CP. Good catch. Good catch. And so this should be C2 and then U2 dot U1 and all the way out to CP UP dot U1. Okay. So what? What does that help us with? It's okay, you shouldn't know this right away. Just give it a look at that a little bit and tell me what more we can conclude.
Well, we do know, well, we know C1U1 is. So we know C1U1 dotted with the set is 0 because you can
Mhm.
rearrange dot products, right?
Mhm.
With your candidate.
Mhm.
So you can pull out C1U1 out of each,
Mhm.
and then you're left with C1U1 times or dotted with, or would it be dotted with a time?
Well,
Yeah.
I want you to just look at these terms and tell me what you can tell me about those. Izzy for the win again. Anybody want to try? What kind of set is this? What do we say in the givens? What do we say at the very beginning? S is a what kind of set? No, that's the thing we're trying to prove. S is an orthogonal set. What does that mean? All the dot products are 0, right? So that means that at this point, we can say that this is 0, and this is 0, and this is 0. Every single term is 0 except the first one. Let's clean all this garbage up so we can work from here.
So why not the first one?
Why is the first one not 0? Because U1 dot U1 is not 0 because this is the length squared.
Yeah.
And U1 is not a 0 vector, so it has some length.
Okay.
Okay, so here's what we've done. We started with 0 equals this. And we boiled all the way down to just really it equals that. So we're saying 0 equals C1 times U1 dot U1. This is really funny that there is literally a connection between algebra studies and advanced topics today, because in algebra studies today, I was teaching the zero product property, right? If 0 equals something times something, then one of the things has to be 0, right?
C1 is 0.
Right, so this is not 0, which means C1 must be 0. So let's write that. C1 must be 0 because we know that U1 dot U1 does not equal 0 because U1 has some length.
Wait, what do you mean by like it has length?
It's not a 0 vector. It's some vector that's non-zero, right? We set that up in the definition of the theorem. We said that we have a set of vectors that are non-zero. So if it was a 0 vector, then we could say, oh crap, U1 dot U1 might be 0. But since U1 is not the 0 vector, then U1 dot U1 is its magnitude squared.
Oh,
Okay. So what is this? Okay, we are literally only 1/p of the way. Did you catch what I just said? 1/p, because there's p vectors. It sounds really dumb, but
okay. Oh,
we are 1/p of the way done with the proof.
oh my goodness.
But look what we've done. All we can say is we can just say now, argue similarly for C2 to CP, and the proof is done. Because how else would you go? You would say, oh, well, let's just do this whole thing again, but write this as 0 dot U2, and then do the whole thing again.
And UN.
Yeah, and do it all the way out to UP, and the whole thing would work. Does that make sense? So C1 is 0, and we will say that C2 is 0, and C3 is 0, and dot, 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 and CP is 0. And we'll just say by a similar argument, and I'm going to put an arrow back up to this whole argument that we did up here. We'll kind of bracket this off and say by a similar argument to right there, right? And therefore we did it. We showed that every single scalar must be 0, and so therefore the set is linearly independent. So therefore, we have a linearly independent set because all scalars are 0. Okay, did I lose you, or what do you think?
I get it, but it's just like, it seems really like, it seems like it kind of came out of nowhere.
It did. That's kind of what's beautiful about these proofs. It's like, look what a trivial statement we started with. I mean, I could have just said to you guys this. I could have just said, okay, guys, every orthogonal set is linearly independent. Leave it at that. Just believe me, okay? But I tried to show you where does that come from, and that's one of the things that I try to touch on in this class a little bit, but not go too far into because it gets a little ugly when we do that. But all we started with was this basic statement, and then with a little bit of algebra on our vectors, we showed that everything zeroes out, proving that C1 equals 0. Questions? So you believe me?
I do.
Every orthogonal set is what?
Linearly independent.
Linearly independent. Good. Okay. Zoom people, any questions? Okay. I've got one more theorem / proof, and then why don't we do some practice problems before we keep going, and we'll take an actual real formal break. And didn't you want to play a game or something?
Yeah.
Okay. All right. A definition. Oh, there goes James. Goodbye, James. Okay, so an orthogonal basis. This is a new term we haven't really heard before. An orthogonal basis. We've talked about an orthogonal set. An orthogonal basis for a subspace W of Rn is simply a basis for W that is also orthogonal. Sounds kind of trivial, doesn't it? But kind of dumb to say that because every single orthogonal set is a basis for something, because every orthogonal set is linearly independent. So now, unfortunately, the real power of this is lost on the fact that we don't have time to cover all of chapter 6. There are these fascinating theorems and facts that come from, ready for this, what in Algebra 1 do you remember doing, you guys remember doing linear regression, right? In Algebra 1 or Algebra 2? Remember the whole process?
I really don't get that.
You don't know what I'm talking about?
We did it on our calculator.
Yeah, on the calculator. That's what I mean.
Oh, okay.
Remember, you would do this. You would go, let me show you.
Like putting it into a table.
Remember that? Yeah.
Yeah,
X,
you make a graph.
Y,
Yeah.
1, 2, 3, 4, and then 5, 4, 3, 2, and then you go. Remember this?
Minus X equals Y.
Yeah, you can come up with it on your own. I know. So look, oh look, guys, they almost form a line, and then your teacher would show you, look, we can actually find that line by doing linear regression, and boom, there's our line. Y equals -1x plus 6, right? Now, this process, oh shoot, I just made the line go at the thing. There it is. This process of finding the line, the subspace, thinking linear algebra, right? Finding the element of a subspace that lies closest to these things. If we abstract that idea out of single variable algebra and into systems with many variables and equations, it allows us to take a system that's inconsistent and find the closest solution to the system, which is super important. It's called doing least
Yeah.
squares.
I mean, we do that with stats.
Yeah. So this process of starting with an orthogonal basis allows us to find a least squares solution. We won't get there because we don't have enough time, but it allows us to find a least squares solution to an unsolvable system. In other words, a system that would be inconsistent if we used ref, but it's consistent if we find an approximate solution. So for right now, this definition just seems kind of trivial, like, so what? Okay, an orthogonal basis, yeah, we can find one. But an orthogonal basis is important for doing even the simple task of projecting. Remember that we learned in multivariable, right? And so we're going to see kind of how that thing plays into that definition. Online questions, anything? Okay, one theorem, one proof, and then we pause for a break. Okay, here's the theorem. Now that we know what an orthogonal basis is, we're going to start with one. So let U1 to UP be an orthogonal basis for a subspace W of Rn. What I'm about to teach you is that we can do an old problem that we studied first back in chapter 1 or 2, I think. We can do an old problem in a new, more formulaic way without rereffing. In other words, we can avoid row reduction entirely. Okay. So let U1 to UP be an orthogonal basis. So far, so good. That's all we've started with. Okay. For each Y in Rn, oh, I'm sorry, for each Y in W, sorry. So for every vector in the subspace, the weights, the scalar weights, that's what I mean by weights, the weights on the linear combination Y equals C1 U1 all the way out to CP UP.
Y, vector Y?
Y, vector Y, thank you, vector Y, are given by, okay, so this is the conclusion of the theorem. So what I'm telling you, we've had problems like this before, haven't we? We've said, can you write a vector as a linear combination of the vectors in a set? We would write the equation and we would ref it, right? Well, now I'm saying that there's actually a direct, quick way to find these scalars without a ref. And here's how you do it. C sub j, I mean, there's P of these, so I can't just say C1, C2, C3, I would be forever. C sub j is found by taking Y dot CJ, no, I'm sorry, Y dot UJ, sorry, Y dot UJ over UJ dot UJ for j equal to 1 through P. And man, that should look a little strangely familiar. And put vector hats on the U's, my mistake. Oh my gosh, what does this look like?
Projection.
A projection. That's crazy. That's so crazy. This means that if you want to find the components, if you want to find the scalar weights, you literally project Y onto U1. And then you project Y onto U2. And if we could visualize bigger spaces, we would say, then you project Y onto U3 and U4, right? And all of those projections give you the scalars that go in front of those, right? So literally all we have to do is we have to just take a couple dot products. We dot Y with the first vector in the orthogonal set and dot the first vector in the orthogonal set with itself, and that gives you your scalar. So I said we're going to prove this. This seems way too hard to prove, but it's not. It's proved exactly like you prove the last theorem. Okay? So just like up above, we're going to take a dot product. I'm going to take Y dot U1. Okay, well, wait. Y is C1 U1 all the way out to CP UP. Because why? Because Y is a member of the subspace. I'm going to dot that with U1. Okay, well, what comes of this? What comes of this is C1 times U1 dot U1 plus C2 times U2 dot U1 plus all the way out to CP times UP dot U1. And everything in this equation becomes 0. This goes to 0, everything except one thing. Everything inside the ellipses goes to 0, and this goes to 0, because it's an orthogonal set. So look at what statement we have. Y dot U1 equals C1 times U1 dot U1. Oh, that looks ugly. That looks like it's like 5 variables and dot products and vectors and all that crap. But remember what this is. A dot product is just a number. And this dot product is just a number. So this very quick proof shows us that the first scalar, C1, is just Y dot U1 over U1 dot U1. And then we take that cheap shot, we say, yeah, we've really only done 1/5 of the proof, right? So we just say, do similarly, and mathematicians do this all the time, do similarly for C2, C3, all the way out to CP. And we show that every single time we're gonna get, like for C2, it's gonna be Y dot U2 over U2 dot U2. Okay? I think that's really, really cool. And the geometry behind this is literally a projection. Let me show you a picture. I promise this is the last thing we'll write. We'll take a break. Let me show you a picture.
Is it the length of the projection that's the scalar?
Yeah, the scalar is the coefficient that goes in front of the vector.
Wait.
Right. You're right. I shouldn't say it's the projection. I should say it's the scalar that scales that vector down.
Oh.
Go ahead. Okay. All right, here's the geometry. Take, you don't understand it?
No, I don't know my question is more. I had something that I was thinking about, but I don't remember why I had a question.
Okay.
We'll see.
Make two vectors kind of long like I just did and make them at right angles because these are going to be an orthogonal set. U1 and U2 form an orthogonal set. And then inside that, I want you to draw a vector y that's about this long. That's vector y. Now, of course, we're doing this in R2. We're drawing in a plane. So this is so lame because we're only in R2. But if you can imagine extending it to 3 space and then to 4 space, this theorem still holds true. Okay? So what I'm telling you is that if we project y onto U1, so I want you to do that by making this and then make a really bold vector right here. That vector is y dot U1 over U1 dot U1 times U1, right? It's this scalar multiple of U1. This is the geometry behind the algebra we did right there. And similarly,
Wait, times U1.
because, right, isn't it? This is the scalar that goes on.
Got it.
And then do another one, do another little perpendicular that goes over here and do another really bold like this. Who's back? Oh, Joanna's here. Excellent. Okay, so then that vector is a scalar of U2, isn't it? Right, so this is y dot U2 over U2 dot U2 times U2. Yes, we're saying a lot of U2 here. Hi, Joanna. We're kind of in the middle of 6.2. I've recorded everything, so if you want access to it, you can have it, all right? Oh, she wasn't in yet. And I just, no, that's not the leaving symbol. That's the they've arrived signal, yeah. Like, no, thank you. Okay, so this is what this means is that red vector, now I know you might not have colors, so that's fine. Red vector is really blue vector plus green vector, which means that vector y equals y dot u1 over u1 dot u1 times u1 plus y dot u2 over u2 dot u2 times u2. It's pretty remarkable that to find the scalar weights that get us to y using this basis, we don't have to reref. Now, don't lose track of what requirements have to be on the set. The set can't be any old set that spans the subspace. It has to be an orthogonal set to make this work. This formula only works when the basis is an orthogonal basis. Okay, which also begs the question then, well, how do we turn an ordinary basis into an orthogonal basis? And that's another thing that unfortunately we will never get to this year because of time and the pandemic and everything else. So let's pause there. That's a good place to stop. Let's take a real 5-minute break, leave the room, go get yourself a drink, take a stretch, and then we'll come back and do a little more work. Resume recording. Okay, we're back recording. The directions say determine which sets of vectors are orthogonal. So the question is this an orthogonal set or not? So Christina, could you tell me what I ought to do to find out if it's an orthogonal set?
Would you have to find the dot product of each and every set of 2?
That's right. So let's label them U1, U2, and U3, and let's just do some quick computation.
U1, U2, U2, U3.
Exactly. U1, U2, is that 0?
Yeah.
Yeah, that one is 0. Check. U1 with U3. -5. That one is 0, right? Yep.
Yes.
And U2 dotted with U3. Yep. So therefore, yes, here we have an orthogonal set. And since it's an orthogonal set, what else do we know? Yep, this wasn't part of the question, but we're going to say it anyway. It's linearly independent, and therefore it is a
Basis
Ba-
for the subspace.
good job.
Oh,
A
okay.
basis for R3. And really, if you want to really continue everything we learned, it's a basis for R3, and therefore we can write any vector in R3 as a linear combination of those by assigning weights to it using the formula that we just learned.
And it's invertible.
Yes, and the matrix would be invertible if you put them in a matrix. Good job. Okay, no need for question 6 because it's the exact same question. So 6 we are going to skip. It is the same concept as above. Or would you like me to assign 8 of those problems that are just no, thank you. Okay. All right, we are going to move on to 9 then. Here's 9. Okay, U1 is the vector 1, 0, 1. U2 is the vector 2, 2, -1. And U3 is the vector 1, 1, 4. And X is the vector 5, -3, 1. Here are the directions. We are supposed to show that U1, U2, U3 is an orthogonal basis for R3, and then express X as a linear combination of the U's. So the point of this problem is to say, can you write X as C1, U1 plus C2, U2 plus C3, U3? And of course, the answer is going to be yes, if U1, U2, U3 is an orthogonal basis. So we're going to check that, okay? We'll just do a real quick dot product. So the first dot product is 0. The first and the third is, crap, did I copy something down wrong?
It's not.
That's because I'm dumb.
Make it -1, 1.
No. I just copied the problem wrong. It's 2, 1, -2.
I think we actually checked.
Oh man, I copied like some vectors from 9 and some vectors for 10. Shoot. Okay, U1 is right. U2 is wrong. I'm sorry. I know. I am an abject failure. Okay, 1, 0, 1, -1, 4, 1, and 2. Right. Okay, there we go. You've given me a crisis of identity. Did I copy the X wrong? I copied the X wrong too. Okay. Just take away my teaching license.
At least you can correct.
At least I can ref by hand, that's right. 8, -4, -3.
Eric, if you're listening to this, please respond.
Well, we'll see if he watches the video.
So that's what I mean. We'll see.
Yeah.
Text us in the group and say, hey, that's not very nice.
That's right, that's right. Okay, there we go, now we're set. Okay, so now are they orthogonal? Yeah, U1 and U2 are. U1 and U3 are, and U2 and U3 are also. Yeah, okay, so we're good. We have an orthogonal set. So what I'm going to do is I'm going to find each of these scalars according to the new formula, not the old rereffing, and we're just going to show that it's going to work either way. Okay, so to find C1, we're going to take x dot U1 over U1 dot U1. Okay, so x dot U1 is going to be 8 plus -3, so it's going to be 5. U1 dot U1 is 2. Did I do my arithmetic right? 8. Yes. Okay, great. All right. New color, purple. This one's going to be x dot U2 over U2 dot U2 times U2. Okay, so x dot U2, -8 plus.
If it's the scalar, isn't it just?
Yeah, why do we need to do right there?
Oh yeah, sorry. Thank you. Okay, so -8 plus -16 is -24 plus -6. I got -27. And then U2 dot U2 is 1 plus 16 plus 1, so over 18. Divide top and bottom by 9, we get -3/2. And then we'll go orange. No, orange is not going to look nice. Let's go pink. No, let's go green. Okay, so for C3, we're going to do x dot U3 over U3 dot U3. Okay, x dot U3. 16 plus -4 is 12, plus 6 is 18. So 18 on top. And then 4 plus 1 plus 4 is 9. So this gives me 2. All right, so my claim is that C1 is 5/2, C2 is -3/2, and C3 is 2. We're going to confirm it with rereffing, okay? Just to link the two methods that we've learned. Oh, crap. There we go. Okay. So insert new page, reref, and it's going to be a what by what? 3 by 4? 3 by 4. Okay, so we're going to go 1, -1, 2, 8, and I use the correct vectors this time. 0, 4, 1, -4, and 1, 1, -2, -3. We did it. Cool. So I'm going to just, yeah, math works. We didn't lie. So I'm going to copy and paste this over just as people can see this in the notes if they look at it. So there we go. Oh, wait, why did that show up funny like that?
You had the
Oh, I had it over it, didn't I? That was not smart. Okay, let's pull that there. And we'll go there, and we'll go like that. There we go. Like never. Should I? How do I find what? How do
It's not
I?
about that. I don't
Is
know.
there a history?
No, I'm pretty sure these are all just files now that are system computer.
Oh, that's funny. I wonder where I could find them.
I'll wait to find it.
Hmm.
I'll find, you don't have Finder.
No, I don't have Finder because it's not a Mac.
Yeah.
Okay, so all I will say is that this confirms the formula from theorem whatever. Formula from theorem 5. I think it's theorem 5. It doesn't matter. From the theorem that we did in class. Okay, cool. So we don't need to do another one of those, right?
Nope.
Easy plug and chug. So 10 is similar. So 10 we will skip. Seen one, seen them all. 11 is the last one that we are going to be capable of doing with where we got in the lesson. Okay. For 11, you really need very minimal. You're going to need like probably 2 to 3 lines. Okay, here's 11. And then how about we stop after this, okay? Sounds good to you? All right, 11. It says this. Compute the orthogonal projection of 1, 7. So we're going to project the vector 1, 7 onto the line through -4, 2 and the origin. So I want to show you the picture of it before we do the algebra of it. You guys don't have to write the picture if you don't want. You don't have to write anything. So negative 4, 2 is 1, 2, 3, 4, 1, 2. So there it is. We're going to talk about this line. Oh, darn it. This line that goes through the orchard. There we go. Okay, we want to project 1, 7 onto it. So here's 1, 7. 1 and then 2, 3, 4, 5, 6, 7. It's a decent scale. So we're going to take this vector and project it. So this will allow us to kind of get like an approximate what we think the answer might be before we actually do it. All right, so that vector right there. Now our book uses a special notation. I'll teach this more next time if more kids are in class. They call it y hat, that little like weird pokey hat. So y hat is the projection of, let's see, why don't we give these vectors some names? What do you say? This is y and this is u. It's the projection of y onto u. Can someone tell me the formula for it then?
It would be, u dot y
Yep.
over u dot u.
Good job. You have a u dot y on the top over u dot u on the bottom. Okay. And of course, times u.
Yes.
Okay, so let's do it. So y dot u is negative 4 plus 14, so that's 10. U dot u is 16 plus 4, which is 20. Ooh, that's convenient. Times the vector u, which is negative 4, 2. So we're going to cut both of those things in half. So negative 2, 1. Does that look about right? Yeah, it sure does. My picture looks really nice. Negative 2, 1. So this vector right here is the projection. And I want to just test this with one other method on the calculator just to prove that this is legit, okay? A long time ago, we learned that there's a 2 by 2 matrix that allows us to do a projection. And you probably don't have it memorized, but I do because I've done this for 8 years. And here it is. That's the matrix that allows us to project onto a line that makes an angle of theta with the positive x-axis. So what angle does this thing make with the positive x-axis? Well, it's doing this where it's got a rise of 2 for a run of 4, right? Is that right? Yeah, that's correct. Okay, so we're gonna find the inverse tangent of 2/4. Inverse tangent of 2/4. It's in degree, fine. That's our angle, 26.5, whatever. I'm gonna store that as yeah. I'm gonna store that as t, and we don't add 90, we subtract it from 180. Right? So we're gonna do 180 minus t to get this angle of 153. So our theta for this matrix would be 153 ... And I'll store that as s. Okay. So if I make the 2 by 2 matrix, cosine of s squared, sine of s times cosine of s, sine of s times cosine of s, and then sine of s squared, that matrix, when it transforms the vector y,
1, 7.
thank you, should get us negative 2, 1. Deep breath. Ah, cool.
Oh, wow.
Isn't that neat? So the crazy projection formula, when multiplied by the vector 1, 7, also gives us negative 2, 1. I think it's a really beautiful thing to see all that come together, right? Like you see this algebra of projection that we've learned with this fairly simple formula. Actually, it leads to the same thing as this projection formula with the transformation matrix. So that was a pretty productive lesson, right? For 8 students? I don't know.
Not anymore. It's like 4.
Not anymore. We're down. Yeah, we're down to a few. All right, I'm going to stop the recording. That's as far